This chapter we're going to be studying the laws of motion, displacement, velocity, and acceleration. All of these quantities are going to be vectors. A vector, if you'll remember from math class, is a number with a direction. Force is a vector. Whether the force is pushing or pulling, forwards or backwards, makes a huge difference as to whether you successfully back the car out of the garage or drive the car into the garage with the garage door down, breaking all the windows and running over your toes. Displacement is a vector. Whether you are 3 stories above where you started because you took the elevator, or 3 stories below where you started because the elevator bottom fell out, landing you in the sub-basement with a crash, makes a huge difference. Velocity, acceleration, spin, clockwise or counterclockwise, momentum, which way you're moving, all of these are nothing if you don't have the right direction. In contrast, a scalar is the kind of number you've been dealing with up till now. A scalar is just a plain number. Temperature is a scalar. It either is 75 degrees and sunny or it isn't. The temperature doesn't change if you turn clockwise or counterclockwise, if you face north or you face south. Time is a scalar. You are either on time or you're not. It either is 10 o'clock or it isn't. Height is a scalar. You're either 6 feet tall or you're not and don't want to play on the varsity basketball team. Energy is a scalar. You either have energy or you're tired and wiped out and need a power nap. Note that scalars can be negative. You can have negative temperature. Heavens knows in Chicago we have negative temperature all the time. It just doesn't have a direction. Displacement is a scalar. It measures how far you are from where you started and where. This is very different from distance, which is just a plain number. Distance is what your Fitbit says, how many miles you've run in cross-country practice. Displacement is where we go to pick you up. So let's say you go for a run. You run half a mile north and you run another half a mile north. What's your displacement? 1 mile north. How far away are you from where you started? 1 mile north. What distance have you run? 1 mile. Easy. If you start making turns, that's when it starts getting interesting. Let's say you're training hard for the Latin Invitational and you run 3 miles north. Then you turn, avoid the traffic, and run another 4 miles east. What's your displacement? What's your distance? Your distance is 7 miles. You've gone for a 7-mile run, but at this point you're all hot and sweaty. You're completely dehydrated. What's worse, you've run into the forest and the bear is making hamotzi lechem min haaretz on you, and you tell the bear, I'm not motzi, I'm shehakol, and you want to call the rescue helicopter to pick you up. How far are you from where you started? You're not actually 7 miles away. Take a look. You started here. You ended here. How far away are you? Draw in your notebook and find. If you said 5 miles away, you know the difference between distance and displacement. After a 7-mile run, you're 5 miles away from where you started, and it's neither north nor east. It is some angle east of north. We'll call this northeasterly because it's not actually 45 degrees northeast. Velocity is the change in displacement over time. For instance, if you run 5 miles around Sheridan Road in 1 hour, then your average speed is 5 miles per hour. But what's your change in displacement? Look, you're right back where you started. Your change in displacement is 0 because you haven't gone anywhere. You're home and you're taking a shower. Your average velocity was 0 because you didn't go anywhere. This is completely different than hitting the road, heading for Champaign, when your average velocity is going to be about 60 miles per hour south and a little bit west, because that's your change in displacement over time. After an hour, you'll have gone about 60 miles and you'll be south and just a little bit west of where you started. Speed is what your speedometer says. It doesn't include important things like direction. Why is this a problem in physics? Well, let's take a good think. You are kept way, way, way late at a game in the city. By the time you get back to CJHS, it's 11 p.m., and then you realize you left all your homework in the school. You have to break one of these windows that never open, get in, get your backpack, and it is 1 in the morning. You're breaking curfew by the time you finally hit the highway and drive home. You are really, really, really tired. And you are so tired, you are carefully going only 50 miles per hour as you go up 94, making sure you're well under the speed limit. The highway's absolutely empty. Nobody's around for 6 lanes, only you, and you're driving very, very, very carefully at 50 miles an hour when all of a sudden you see blue flashing lights up ahead of you, you get pulled over, and this cop is screaming his head off at you. He's threatening you with detention and disembowelment. He's going to take away your license forever. And you're like, officer, I'm sorry, I don't understand. What's the problem? I was going 50 miles per hour in a 55 miles per hour zone. I wasn't speeding, I wasn't weaving, I was staying in my lane. What's the problem? The cop is screaming and screaming and screaming at you. You idiot. Are you drunk? The cop makes you walk the line. You're like, cop, I swear, I'm clean. What's the problem? What have you done? What have you done that's so bad? You're not speeding. Think about it. Write down the answer in your notebook. It's the difference between speed and velocity. Anybody? Anybody? Bueller? You're going 50 miles per hour north in the southbound lane, genius. You're going in the wrong direction. That's the difference between speed and velocity. In physics, we want velocity. We want to know whether you're going in the right direction before we start worrying about your speed. Quick check-in. Velocity actually comes in 2 kinds, average or instantaneous. Instantaneous velocity is the one we want. It's what your speedometer says. You are going 45 miles per hour. That's great, only the speed limit is 25. Slow down. It is exactly what you're doing right now. It's the rate of change of your position, where you're going. Calculus doesn't believe in any other kind. You can find average velocity with a radar gun, zap. You can find it on a graph, or you can find it with a formula. Average velocity is the one that is the change in displacement over time. Do not write that formula down because it's an average over your whole trip. Find your average velocity on your next commute just for a lark. Look up on Google Maps the distance between your home and the school. Find the time it takes, divide them. Then ask yourself, does that number have anything to do with what was on the speedometer at any time, or even most of the time during your ride? Especially if you take the train and you spent a lot of time waiting at the station. Velocity tells you how fast you're going and where. Acceleration tells you whether that number will change. You can be going 65 miles per hour straight forward and have no acceleration at all because you're on cruise control and you've stayed going 65 miles per hour the whole time. Acceleration is change in velocity over time. It could be a change in your speed. It could be a change in direction. That's the definition of acceleration, anything that changes your velocity. Name 3 ways you can accelerate your car. Put them down in your notes. Your car actually has 3 accelerators. One is the gas pedal to speed you up. One is the brakes. That's an accelerator too. They're changing your velocity by slowing you down. The steering wheel is also an accelerator. It helps you turn. Please note that there is no scalar for a change in speed. Acceleration is a vector. It is always a vector, and it fundamentally has to do with whether or not you're going in the right direction. 3 definitions in a formula don't seem a lot to go by, so we're going to start looking at displacement, velocity, and acceleration graphically. It would be nice if we could get more than one piece of information off of each graph. Let's start with a displacement graph. It shows you start here, you end here. What information does it give us besides the displacement? Well, it looks like a straight line graph, y equals mx plus b. B looks like the y-intercept, that's where we start. What about the slope? The slope, we've got change in y over change in x. Looks like it's going to be our change in displacement over time because we don't have a y, we don't have an x. We've got a displacement We've got a time. Wait a minute, sound familiar? Let's check the units. Our slope units are meters over seconds. Pay dirt. What information does the slope of a displacement time graph give us? Write it down. You got it. It's the velocity. Let's try something similar on a velocity time graph. The intercept tells us our starting velocity, how fast we were going, and in which direction when we started. What about the slope? We've got change in y, only we don't have a y, over change in x, only we don't have an x. Aha! There is our slope. And our units are meters per second divided by seconds. Wait a minute. Dividing by fractions is easy as pie. Flip the second and multiply. The second is this one here. We do not flip the first. We leave the first where it is. We flip the second and multiply. And when we do, we get meters per second squared. What information does the slope of a velocity time graph give us? Write it down. This is one of the formulas we recognize. The slope of a velocity time graph is acceleration. The slope of an acceleration time graph looks like it's going to give us meters per second cubed, and I've never even heard of meters per second cubed. Instead of looking at the slope, let's look at the area under the graph. At any given time, it looks like that area under the graph is going to give us a nice rectangle. The area of a rectangle is base times height. There's our base. There's our height. So our area is going to be acceleration times time. That's going to be meters per second squared times seconds. What does meters per second squared times seconds give you? Said it myself. Meters per second. The area under an acceleration time graph tells you the velocity. The longer you go, the more you accelerate, the faster you're going. I bet we could do that with a velocity graph too. Take a look at the units. We've got meters per second times seconds. Y-axis, x-axis. There's our unit. The area under a velocity time graph tells you the displacement. Now you're ready for your lab. Answer the questions on Edline to make sure you remember what displacement, velocity, and acceleration mean. We are going to break out those motion sensors and we'll see what they actually look like.